to hear from the audience also, because I have not attended the sessions fully. So register location using graph coloring was covered, I believe, and software pipelining, then writing LLVM passes. I'd like to know like what are the things that you've done in LLVM passes in the last week, like tutorial, like it's on LLVM IR. Then you studied SSA form, like in LLVM passes, like you convert one input intermediate IR1 to a modified IR2, and IR1 and IR2 they should be typically semantically equivalent, and LLVM IR has instruction like add, merge, etc. Here the difference is with respect to LLVM backend or a compiler backend is add, merge are like independent of the hardware that is target. Like it's LLVM IR is target independent. So when we slowly move to this backend, when there is hardware independent IRs are there, how this last stage of coordination, that is last stage of compiler is done, we'll see in the lecture. So you might have seen this code, something similar in LLVM IR, where we have a function, run-on function in the LLVM class, where you iterate our basic blocks in the function f, and then you print here is ERRs and print the basic block name. Then for instruction I, you print all the instructions in the basic block using I.down. So this is the LLVM IR that have maybe you worked on the LLVM passes. You might have read codes something similar to this. Then you run the LLVM passes with the opt tool, and then or run your LLVM passes with opt tool. Then in this lecture we'll look at an introduction to LLVM backend. Then some fundamentals that is required for a code generation to be understood, and then fundamentals like register assignment, code generation for expression, code generation for loops. This will be covered. Then some peephole optimization. Then we'll slowly move to LLVM code generation, the second part, where you look at the peephole optimization with a specific example with respect to the hardware. Then you have instruction selection, like for a given hardware independent instruction, the LLVM IR, like add, merge, etc. Which instruction to be selected for the given target. Then running MIR passes, like LLVM has an intermediate code called MIR, that is for the machine that's called machine independent representation, and how you work on that. So coming to code generation, so we look at this code generation is code generator is different for each target hardware. So different hardware has different instruction set, different addressing mode, register set, etc. So latency associated with instructions are different, and of course you are aware that add and merge, like if you look at merge, it has more cost compared to add. So similar differences are there with the instruction set. As hardware become complicated, the number of instructions it will become more. So code generation, proper optimized code generation set of tasks. So LLVM has a machine intermediate representation. It's called MIR for the backend passes. I worked with LLVM IR, that is called a midlane pass. Then SSA form is a generic intermediate representation used in many compilers like CLang, GCC, etc. So, so we will be not looking into SSA form, but this SSA like is generic. So instruction selection, register allocation, peephole optimization, etc. are part of compiler code generator. This also like the pointed out here is this is generic to all compilers, even for CLang or GCC. Instruction selection, register allocation, peephole optimization, etc. are present. So in this first part, I'll cover this process with concepts of register allocation and peephole optimization, independent of the tool like LLVM. But before going to that, like look at this LLVM MIR code. So in LLVM IR, we had run on function. Here we have run on machine function. and the argument to that is machine function as a class, and then you have machine basic block as another class. Then you can have mbb.getName. So there is a lot of similarity with respect to LLVM passes that you run, but of course there is also some differences. So that will cover in the second part. So compiler optimization, I hope you have this covered, like machine independent optimization, like dead code elimination, common sub-expression elimination, loop invariant code motion. All these are machine independent optimization which can be done on LLVM MIR. There are some machine dependent optimization like machine IDMs, peephole optimization, register allocation and assignment. These things are specific to each hardware, it's different. So you are going for a backend where it is machine dependent. So the lecture will be based on that. So for this lecture, we'll assume that you have a simple machine, and we are covering the part with independent of LLVM IR in the first half. Then we'll move to the LLVM part. So first half, we'll look at this simple machine model. So feel free to ask any doubt in between if you have. And machine has n registers, so R1, R2, etc. Rn. Machine has load and store instruction like load from memory, store to memory. Machine has arithmetic instruction like add, mul, etc. And machine has conditional and unconditional jump instructions. So machine has direct, immediate, and indexed addressing modes. This is not that important, but the first parts like registers, load, store, arithmetic, and conditional instructions, they are important for this lecture. And this machine model will be assumed for the coming slides. Hope it's clear. So in this lecture, we look at optimal code generation for expression. So each node of an expression tree has a number as label. So these numbers are sometimes called Hershov numbers. So consider a model where each expression tree, where all leaf nodes have label 1, label of interior node with one child is label of the child, and label of a node with 2 children is larger of label of the children if labels are different. And 1 plus label of children if both children have the same label. Got it? So for this expression, a minus b plus e star c plus d. So you can imagine like what will be the expression tree. So first a minus b will be evaluated, then c plus d. Then you have star coming with a higher precedence, so e star c plus d will be evaluated. Then plus. The point here is that these expression values need to be stored in temporary registers or virtual registers that you have seen in LLVM pass also like %1, %2. So these temporary variables are not present in the actual code. So this is the expression, final expression. Like first you evaluate a minus b in a virtual register or a temporary register like t1. Then you have t2, that is equal to c plus d. T3 is e star t2. So e star t2, you can see like this. So t4 is t1 plus t3. So if you draw the expression tree for this, it will be like this. So here a, b, e, c, d. So here you have to finally convert it to a machine code with optimal number of registers being used for this expression evaluation. Optimal number of registers, you have to convert these virtual registers to the actual machine physical registers. So physical registers, I already mentioned in the machine model, there are n registers. So how should a code generation algorithm should be done so that you use optimal number of registers? So C D. T2 is not a part of the actual high-level language code or the intermediate code, you can say. So T2 is a temporary variable. It could be a placeholder for a register. T1, T4, T3, T2. If you look at this, it can be done with 4 registers without much trouble. A minus B can be in one register. This T1 can be in one register, T2 in another register, T3 in another register, T4 in another register. That's like a very naive code generation, but you want the number of registers to be optimal. For that,
sorry to interrupt. I did not get how you came to 4 registers.
So, like if you have say R1 equal to A minus B can be done in R1. This is A minus B actually. This is a temporary holding. This A minus B. So it's R1, R2, R3, R4.
Wait. So wouldn't you first assign A and B to individual registers, then pass them through the ALU and then store A minus B? So you need 2 registers for A and B both, rather than 1 for T1.
Yeah. So the thing is, you have to load into the registers. Like you are correct. Like A and B need to be loaded into the register. Then you do a computation. So add and null I explained in this sample machine where I didn't explicitly mention the semantics. We'll be coming to that in the coming slide, like how that is done. So I randomly told a number like 4. You can do even without lesser than that, like with a less number of registers. 4 is not the optimal one. You can have less number of registers. With even lesser number of registers, it may be possible. So
yes, but I still don't understand how we came to the number of 4.
Yeah, I just randomly told like it should be possible with 4 registers. So since so if you look at suppose we are storing A minus B in one register, T plus D in another register, and E star T2 that is in another register, and T4 in another register. That's what I told for a random a naive answer.
Okay, thank you.
But this is completely unintuitive that A minus B will be stored in one register. So I'm also not getting how to.
Yeah, I'll come to that.
Okay.
Only for the question here. So this so in this case, what will be the label for this? So as per this algorithm, I mentioned like label of all leaf nodes have label 1. Label of integer node with 1 child is label of the child. Label of the node with 2 children is larger of label of the children if labels are different. 1 plus label of children if both children have the same label. This is clear, right?
Yeah.
Yeah. So here I would like to know what will be the label, like for A, B, E, C, D. What will be the label?
A, B, C, D, E will be at 1.
Yeah. Then T2.
T2 will be 2.
Yeah.
Because these are different, so we will add 1.
Yeah.
Then E is 1, T2 is 2. So T2 will be 3. T3 will also be 2.
Yeah.
And T1 is also 2.
Yeah.
Since T1, T3 are 2, T4 will be plus 1. So
yeah,
3.
Yeah. So A, B are 1 leaf nodes. A, B, E, C, D all have 1. T2 have like label of 2 because both the children have same label 1. But for T3, left child has a label of 1, right child have a label of 2. You take the maximum, that will be 2. So T1 will have a label of 2, A, B, since both children have label 1. Now T1 and T3 have label 2, so T4 will have a label of 3. So the intuition here is that you can do a optimal code generation based on the algorithm that can cover it using 3 registers. Suppose you just briefly remember this machine model. Machine has n registers, load and store instruction, arithmetic instructions. We are not worried about which are all exact number of exact instructions, like how many how many arithmetic instructions are there. We are not worried too much, like add, merge, sub, etc. are there. Then So now what will the code generation algorithm like? Assume root node has label k. The machine register RB2, RB plus k minus 1 are available. So B is like a number which is greater than 0, that is from 1 to n. For that is will be different for each node. So initially you have registers from R1 to Rn. For each node, it has a label and a machine register RB to RB plus k minus 1 that are available for a node. For that node, this much registers are available. So if B is 2, then k is 3. Then what will be the registers available? B is 2 and k is 3 means like you will have 2 more registers. So B is 3 means R3 and R4 will be available if k is 2. Any doubt on this? So to generate code for node with both the children having label k minus 1, like as you have seen in say T2, which has A and B as child, having label k minus 1, recursively generate code for the right subtree with k minus 1 registers. The result will come in RB plus k minus 1. Recursively generate code for left subtree with k minus 1 registers. The result will come in RB plus k minus 2. So just note that for a root node with both children having label k minus 1, first you generate code for the right subtree, and the result will come in RB plus k minus 1. Then recursively generate code for left subtree with k minus 1 registers, like result will come in RB plus k minus 2. So then generate the instruction OP, that's the instruction associated with that expression. Then RB plus k minus 1, RB plus k minus 2, RB plus k minus 1. So this will be the generated code for that node, which has label k. So generate code for a node with children having different label. Generate code for big child. Result will come in RB plus k minus 1. Note that B is greater than 0. Does not start from 0. So suppose B is 1, then it will be RK. B substitute B for 1 is in every place. If you substitute B as 1, then it will be RK. Result will come in RK. Generate code for other child. Result will come in RB plus L minus 1 with L less than M. So if you look at the both the node having label, both the children have label k minus 1, assuming B is 1 means right subtree it will be coming in RK minus 1, RK, because if B is 1 means is minus 1 and B will be related to 0 if you put that. And RK, you have the right subtree, RK minus 1, you have the left subtree, then you have, this will be like RK minus 1, RK. And this for second part is generate code for node with different labels. So you can, as you can see, like here we are not going for right subtree. First you generate code for big child. The child have biggest label, and the result will come in RB plus k minus 1. So then generate code for other child. The result will come in RB plus L minus 1 with L less than M. Then generate instruction RB plus k minus 1, RB plus L minus 1, RB plus k minus 1. So any doubt on this?
What is M?
Where is M coming?
In the second last line, you said that we generate code for the other child, and the result comes in RB plus L minus 1 with L less than M. But I didn't see M before.
That's L less than K. Sorry, that's a typo, L less than K.
Okay, so from what I understand is that when you generate code for the big child will consume the larger number of registers, right? So
yeah.
So we allocate our B plus K minus 1 registers for the big child, and then we override those. Once we have computed the big child and stored the result in the final single register, we deallocate all those registers and use them for the other child. Is that correct, or do we allocate new registers?
Thing is, if once you evaluated the left, right, one part of the child in one register, result is available, the remaining registers can be used because you have computed the value for that subtree, right? One subtree means the registers that are used for the subtree, its values are not that relevant. Only that top, that result register is relevant.
Okay.
So you come with that example here. Like, for example, we have this T2. Okay. So what was T2? Okay, I have to go back. T2 is C, D, right. So what is the right subtree is D, left subtree is C, and both the nodes have same label. So both the children have same label. So what you'll do? Generate code for right subtree, generate code for left subtree, and the result will be stored in register which is used for, or which computed the result for right subtree. Am I right? So if you start from root node T4, T3 will be computed. That register will be computed in a register. That register will be used to store the result of T4. You got it? Is it clear?
Yes, but this algorithm is meant to minimize the register pressure, right?
Yeah.
And it comes at the cost of performance. If I want to parallelize the computation of this entire tree, then I cannot do this.
Parallelize in what aspect? Like if you're considering about the multi-core machines or what? But it's or you're talking about the software pipelining or instruction level parallelism.
No. Let's say that you have a superscalar processor, and a superscalar can execute 2 threads, or you can compute 2 simultaneous expressions in one go. Then in that case, this will not work.
Yeah. So superscalar means you're telling about software pipelining. No?
No, software pipelining is different. Superscalar means that you have 2 dedicated execution units.
Yeah. Okay. We are, as I already mentioned, the machine model. Okay. So this like you're assuming like only one arithmetic logic unit. So to make the example simple within 1 hour lecture. So here, you're right. So load R3 is the right subtree of the T2. So what for your question I answered like, so superscalar it will not be optimal, but we are assuming only one arithmetic logic unit. Is it clear?
Yes, thank you.
Yeah. So R3 is loaded into D. That is the right subtree of T2. Then R2 is loaded into C. This is semantics of the arithmetic instruction, like destination register, source 1, source 2. So now R3 holds the value T2. And now R3 holds the value of T2. R2 is now free. Now to compute T3, you load into R2 the value of E. Then again use mul R3, R2, R3. Then you get the result in R3. So R2. So if you look at the label of T3, it was 2, and we have used only 2 registers up to T3. Because we have used R3 and R2. Yeah. Now, in the case of T3, that is done. Then now you have to compute T1. So you note that R3 is required for the next computation to compute T1. So you load A and B in R2 and R1, then subtract R2, R1, R2. So here now R2 holds T1, R1 is free, and R3 holds T3. Then you add R3, R2, R3. You got it in T4. Value of T4 is computed in R3. This is for an expression. Is it clear?